Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to this series of lecture on elements of solar energy conversion. We are almost closing to the end, and today we are going to continue talking about the photovoltaic conversion mechanism, and today here we are at lecture number 34. So, in the last class where we stopped, we have looked at the minority carrier injection, right. So, due to the p-n junction diode, and if you apply a small potential, okay, for forward bias potential, then you have some carrier injection in the minority side, right. That is called minority carrier injection. So, for the N side you have increase in concentration of holes, and that happens at the space charge region edge, and for the N side we know, or we have designated that location to be x n, and that value is dependent on the equilibrium value of hole concentration in N side multiplied by exponential q V a over k T minus 1, right. So, this is the carrier injection happens, and you can see that it depends on the applied voltage. And similarly, for electrons, and of course that will be in the p side where it is the minority carrier, there we will have this del n p, and the space charge region edge in the N side is minus x p. So, that will be n p naught exponential q V a over k T minus 1, right. So, I mean similar procedure you can follow and you can obtain this particular expression. And it is important to note that minority carrier concentrations are significantly affected. I stress on the word significantly affected under forward bias condition, right. But the majority carrier, of course, they are also affected, and amount wise they are equally affected, because it has to be mass balanced. The total number of holes or electrons are not getting changed, there is no generation, no recombination so far. So, only due to bias what we have the same amount of holes going from the p side to the N side, and there the minority carrier holes they are significantly affected, but the majority carrier concentrations are not significantly affected, we can say, because the carrier concentration itself was higher to start with, and that is why little bit of decrease does not matter. Okay. Now, you can, from the expression itself, you can say the carrier injection happens as long as the potential is applied, right. If you take out the potential, then that carrier injection will go away. Now, this carrier injection, it is causing larger concentration of the minority carrier at the edge of the space charge region. Isn't it? And in the quasi neutral region, where there is no field, okay, that means xi is equal to 0. So, there will be no drift current, right, and under equilibrium the diffusion current also does not exist. Because in the quasi neutral region there is no gradient of these concentrations. If there is no gradient, there will be no diffusion, right. So, under equilibrium it does not, but once you increase the space charge region edge concentration, so there is a gradient that you are creating. So, the carrier injection is creating a concentration gradient in the quasi neutral region, right, because one edge you have altered the concentration for. Okay. So, that means diffusion will occur. Let us first try to understand this qualitatively, how this carrier injection is going to affect the currents. Okay. So, you can qualitatively say that if this is the p-n junction, where this is the space charge region, you have this p side, n side, and here you have space charge region. Then in the p side, where the electrons are minority carriers, you have a larger concentration here. So, you have a concentration gradient created at the edge of the quasi neutral region. Okay. So, this is the electron concentration gradient, okay, created, and similarly you can have some other hole concentration, it does not have to be equal, and in the n side you have this hole concentration gradient, right. This is the result of the carrier injection. So, whenever under equilibrium itself, under equilibrium as well as under forward biased condition, under forward bias condition, this recombination happens, okay, with some characteristic lifetime. this we have seen before. So, in the continuity equation, the general form of continuity equation is this. If we write it for the minority carrier in the p side, that means for the electrons, right. This we have seen earlier, we are just restating it. So, under steady state, this term will be 0, right, and if there is no generation, that means no light falling on the diode, that term will also be 0. So, under no light condition, no light or any form of energy going in. So, that will not generate anything. So, what terms we are left with is this term, right. So, we have will be equal to N p divided by tau n. Tau n is the characteristic lifetime for an electron. Okay. So, this is the continuity equation form. So, this is the continuity equation for minority carrier in the p side. Now, just by definition of this J n is q d n into d n is the capital D n is the diffusion coefficient, right, and then the gradient term, and here I should write n p x dx. Okay. Everything we are talking about in the p side only, the same thing can be done for the other side. Okay, and this is by definition, right. Now, so if we put this in continuity equation, then what we get? We get the governing equation for the minority carriers electrons in the p side. And this d n tau n, this is the diffusion coefficient multiplied by the characteristic lifetime. You can see that it gives us a unit of length squared. Okay. If you look at the units, so you can as well write it in terms of L n squared. Okay. So, L n is what? L n is the basically L n is nothing but this d n tau n square root, and it is called diffusion length for the minority carrier, right. So, what we obtained here is the governing equation. So, this equation is the governing equation that dictates how electron concentration in p side of the diode will vary with the length from the edge of space charge region, right. So, earlier what we have seen that if this is the space charge region, you have some concentration and it will vary. So, this governing equation tells us the, so basically the form of this variation is obtained by solving this governing equation. Okay? That is the purpose, and that exact form is important because then only we can quantify it. The concentration gradient form will tell us how the diffusion happens. So, it is important to get hold of it to exactly quantify the diffusion current. Now, this governing equation is second order ODE, ordinary differential equation, right. You have only one dependent and one independent variable. Independent variable is the length x and the dependent variable is delta NP, right. So, the second order ordinary differential equation will require two boundary conditions, right. This you are familiar with your math background. So, what we can have, the first boundary condition that we have is at the space charge region itself. So, and that is x equal to minus xp, because we are talking about the p side and the space charge region stands where x is equal to minus xp, and it is known, right. Rather delta NP is known from the carrier injection, right. We have quantifiable or quantified value of delta NP at the space charge region edge. Okay. And what is that value? Delta NP is equal to or at minus xp is equal to NP naught exponential qv over kt minus 1. So, let us not use VA anymore, we do not have to say applied explicitly, that is the only voltage. So, we are going to use V. So, here a small note that VA is being replaced by V, as no other voltage is present in the expression. So, there is no confusion. Earlier we had to do it because we had to differentiate that applied voltage from the built in voltage. Okay. So, now we do not have that built in voltage anymore in the expression. So, we do not have to differentiate by explicitly telling it is VA. Okay. So, this is the space charge region delta NP, and the second boundary condition that we have is as x tends to infinity, that means deep into the quasi neutral region, what you have? You have this tends to 0, because there will be no effect of the carrier injection deep into the quasi neutral region. So, that you can say x tends to infinity, your delta NP tends to 0. So, the boundary conditions you have, the governing equation you have. So, you can find the solution of the GE, the governing equation under this boundary condition, which is delta NP x, that means it is a general variable x now, and that is equal to delta NP at minus xp, okay, and then this exponential function of x divided by ln. So, you can try this by yourself and you can see whether you are getting this solution or not. Very straightforward, from your high school days differential equation understanding, you will be able to solve it. Okay. Now, we can put this value of the pre-exponential factor, okay, which is NP naught e to the power q v by k t minus 1, then exponential minus x ln, right. So, that is the complete solution of that concentration gradient. So, it gives us the form how that variation happens. Now, let us go back to the p-n junction diode. Let us look at it again. So, again this is the space charge region, okay, and we can see that this is x equal to minus x p and this is x equal to x n, right. Now, for the p side, so this is the p side and this is n side. So, for the p side, the delta n p happens like this, okay, and for the n side delta p n. So, this is basically this is delta p n as a function of x, is not it, and this one is delta n p as a function of x. Now, you can see the direction of these two changes for delta n p and delta p n are in opposing direction, right. So, if you fix your origin here for the delta n p, then let us say that the x is increasing in this direction. So, let us use a new symbol x 1, which is opposite to the direction of x, and on the other hand, if you fix origin here, you name this coordinate system x 2. Okay. So, this is just to ensure that we have taken two opposing direction as the independent coordinate to analyze the delta n p x and delta n p n x in similar fashion. Otherwise, we always have to bother about the sign. So, here the different x 1 and x 2, it is ensuring that as x 1 or x 2 go up in magnitude, the delta n p or delta p n also, I mean it goes down. Okay. That kind of assurance is obtained if we have different coordinate system. That is the only reason why we are choosing x 1 and x 2 instead of a single x. Okay. So, now in this new coordinate system, what we can write? So, for the new coordinate system, what we can write is delta n p. Now, x 1, you note that we did not use x, but we have used x 1. This is n p naught e to the power q v by k t minus 1 into e to the power minus x 1 divided by L n, right. So, please note that x 1 is introduced and you do not have to bother about the sign, because that is the sign you have used earlier. Okay. So, if we put these in the expression of the current due to minority electrons in the x 1 direction, we have this q d n d of delta n p x 1 d x 1. Okay. This is the definition of J n. So, now we can we know the delta n p variation with x, we quantifiably know. So, what we can write? Q d n and then 1 over minus L n n p naught e to the power q v by k t minus 1 e to the power minus x 1 by ln. So, this ln comes from the differentiation. Okay. So, we just straightforwardly differentiated delta n p x 1 expression with respect to x 1. Okay. So, similarly, for the other side, that means for the n side we get the current due to movement of minority holes, right, and we can write the similar expression J p. Now, we will have x 2, right, is equal to, now as it has a negative or the expression, the charge is negative for holes, what value you will get is with a negative sign d p minus L p p n naught e to the power q v by k t minus 1 e to the power minus x 2 by L p. Okay. So, you agree to this, we just use the same thing, x 1 and x 2 are consistent with the current direction. Okay. So, now we know the explicit expressions for the minority currents in both the quasi neutral regions, and that under a certain potential V. Okay. So, for the forward bias V is positive, for the reverse bias V is negative, but the expressions everything stays just as is. Now, that is the expression we obtain for quasi neutral region. Now, what happens to the space charged region, right, because if current flows through the diode, it has to pass through the space charged region as well, right. So, what happens there? So, standard assumption is that the recombination does not happen in space charge region. Why it is a standard assumption? I mean, why we can take this assumption? Because the space charge region is also called depletion region, right, and depletion region why? Because the minority carriers are less in number in the space charge region. So, it is also called depletion region because it is depleted of the minority carriers, right. Why it is depleted of? Because you have a potential there, xi is not equal to 0, and all the minority carriers that will come into that space charge region will be sucked into the other side, right. So, that is why the depletion, it is called a depletion region, and that is why if you have less number of or no number of minority carrier, how can the recombination happen? So, even the recombination term you can neglect from the continuity equation. So, now if we look at the continuity equation, okay, this delta n, again we are writing it for the electrons, and similar you can write for the hole. Right, this is the form of the continuity equation we have used earlier also. So, now we do not have this term which is due to steady state, okay, and we do not have this term due to no light condition, okay, and this term is also 0 because it is depletion region. Right. So, what we are left with is just only single term, and that is equal to 0. So, what we have this del j n del x equal to 0. What does that mean? That j n is constant in the space charge region, is not it? So, we get a very simple expression, it is constant, and what constant it is, that is very easy to find as we see next. Now, you think of the p-n junction diode like this. Okay. Let us say in this axis we are just plotting J, and that J may be due to, and J is for the minority current, okay, minority carrier. So, we will see that right now. So, let us draw the space charge region here, okay, and this is the direction where x is plotted. Okay. So, here again just like earlier, this is minus x p, this is x n, and we have seen that we have used x 1 in this direction and x 2 in this direction. Okay. So, from the given expression that we obtained after solving all those equations, first the continuity equation, first the governing equation for the concentration profile, and then the continuity equation, the current expression that we obtained we can draw in this fashion. So, as the concentration profile flattens, your current will go to 0, right. So, current is going to 0 deep into the p side. So, this is the p side, and this is nothing but the minority carrier current, and in this case minority carrier is electron. So, this is the electron current. What you can write then? You can write it to be J n, right, and on the p side you will have some other value, let us say this, and you will have the same thing. So, again it will go to 0, you can extend this axis, and again it will go to 0 as you go deep into the quasi neutral region. In this case this is n side, okay, and this is the minority current, minority carrier current, and this case they are holes, the minority carriers are holes. Okay. Now, the space charge region we have not touched yet, right. So, what will happen? We do know that it will be constant throughout the space charge region. Now, whatever constant happens at the edge, we can extend that, okay, this will be the constant throughout the space charge region, then only the boundary condition is matched, right. So, that is the J n in the space charge region as well, and similarly you can find the same constant value corresponding to J p. So, this is Jp. Okay. So, both Jp and Jn are constant, but they are different constants, okay, in the space charge region, and those constants they get smaller and smaller as you go deeper into the quasi neutral region, both for p side and n side, and that is how the minority current looks like. So, this is the above picture is the minority current profile across the p-n junction diode, right. You agree to this? Now, if you look at the space charge region only, okay. Space charge region you have the, that is all the carrier you have, right. You do not have any other carrier because those have drifted out. So, in the space charge region the total current would be this Jp plus Jn, right. And more precisely what we can say, Jp at x2 equal to 0, that means the Jp in the minority side, and Jn which is x1 equal to 0, and again that is also minority current, right. So, now if we redraw that thing in a bigger scale, and now I am not using so let us say that this was the or I can use this current also. So, this was the case for the electrons in the p side, right. So, and this was the case for holes in the n side. Okay. Now, the total current in the space charge region will be summation of this and that. So, let us say it is somewhere here. Okay. So, if that is the total current, and total current cannot be different in different region, right, it has to be equal everywhere. So, you can extend this line in the p side and in the n side to get the total current across the p-n junction diode. So, this is total current, okay, and these are, this is minority current, right, and this one is also minority current. Here we are plotting J, and different plots will give you different J. Now, what we are left with is the majority current. Majority current does not apply for the space charge region, right. So, majority current only in the quasi neutral region. So, what you can write here, that if you subtract the minority current from the total current in the quasi neutral region, you will get the majority carrier current. Okay. So, this will be okay. This is the majority carrier current, because this is now in the n side. Okay, and similarly we can draw that for the holes. Okay. So, this is the majority carrier current in the P side. So, that gives us a complete picture of how different carriers are contributing to the total current across the p-n junction diode. So, on the left hand side you can see the majority carrier is shown by this blue plot, okay, and in the this is the P side. Let me explicitly write it. This is P side, this is N side, and this is phase charge region. Okay. So, majority carrier is important and it is carrying the maximum amount of charge, and in the P side it is hole, okay, and electron is the minority carrier in the P side. In the space charge region, that minority carrier contribution or majority carrier contribution does not exist. So, minority carrier contribution just stays the same, okay, and from there we continue in the other side of the quasi neutral region. Okay. So, now if we, so that is the qualitative picture we obtained. Now let us get back to the single independent axis in the sense no x1 and x2, but only one x. So, for that we need to do little bit of adjustment in terms of coordinate transformation, right. So, what we can write that J total is equal to J p at x2 equal to 0, and we have to use minus for x1 because now as x1 and x are opposite to each other. So, basically what we did, we have used a single x here. Okay. So, this single x is giving us this adjustment of the minus sign. Okay. So, this is for coordinate transformation from x1 to x, okay, nothing else, and we have obtained the expression for Jn and Jp. Now, if we put those values, what we get? We can simplify. So, dP by Lp Pn naught plus dN by Ln Np naught multiplied by e to the power q v by kT minus 1, right. Do you agree to this? I mean, please do the algebra by yourself and make sure that you get this expression. Okay. Now, this J total is nothing but your current density, right. So, this is I over A. Okay. So, I over A is your J total. Now, earlier we obtained that I equal to I naught e to the power q v by kT minus 1. This we obtained before going quantitative. Analysis gave us this, right. So, now what we got, this I over A is q dP by Lp Pn naught plus dN by ln np naught e to the power qv by kt minus 1. Okay. So, we got now. Now, if you compare, so if you compare what you get, I naught is nothing but qa multiplied by dn ln np naught plus dp lp p n naught, right. That is what we get straightforward way, and this np naught and pn naught you can further write in terms of the concentrations. Okay. np naught and pn naught can be written in terms of concentration, okay, of dopant. What I mean is np naught is nothing but the intrinsic carrier concentration squared divided by the concentration of acceptor elements, okay, and Pn naught is Ni square divided by Nd, which is the dopant concentration. Okay. So, if we replace those values, what we can get, this I naught qa dn by ln Ni squared divided by Na plus dp by lp Ni squared by Nd. Okay, I naught we did not know that what would be the expression. Now we have it. So, we get the expression of I naught, which we could not obtain by qualitative analysis, right. So, now we have obtained in terms of material properties. So, what I mean by material properties, because all these dn, which is the diffusivity or diffusion coefficient of electrons in the material. Okay. If it is silicon, then silicon. So, that is the diffusion coefficient of electron. dp is diffusion coefficient of holes. Okay. dp and dn, they are diffusion coefficient for electrons and holes, right, and ln and lp are called the diffusion length, which has the diffusion coefficient and characteristic time of the recombination, right, which is also called lifespan. So, that diffusion length takes into account those information. So, ln and lp, they are also material property. So, this is material property, these are also material property, and Ni is of course the intrinsic carrier concentration, intrinsic carrier concentration, that is also a material property, isn't it? And Na, Nd are also material property in terms of those you can control. Okay. The amount of dopant that you put in p side or n side, those are controlled. So, these are dopant concentration, controllable parameter. And Q is the charge of electron, A is the area. Area is of course controllable, that gives you I naught. So, there is a complete like skeleton how we can obtain this I naught is obtained now, and this I naught is nothing but the reverse saturation current. Right. So, it is fixed for a fixed p-n junction diode. So, p-n junction diode, I mean the p and n part, they are obtained by particular dopant by doping those elements. So, once you have fixed that dopants, there is no way you can change this reverse saturation current, that is all it depends on. Okay. And this particular expression it is called the dark IV equation. IV is for current voltage equation for any device, any electronic or electrical device, this VI characteristic curve is very important. So, we are trying to get there, and this VI equation is only applicable when there is no generation or any light falling on that diode, right. So, that is why it is called dark, under no light condition. So, if you follow how we proceeded with first understanding the equilibrium where there is no voltage. If you just bring them P and N together, what happens inside the band structure and all, and that is how we got the equilibrium. Now, once you get the voltage applied, so forward bias, reverse bias, how does that affect? That is what we got, and this is the pinnacle of that analysis which gives us the dark IV equation. And in the next class, we will look at when you apply light, how the photovoltaic effect generates and how you get some current. So, let us stop here in this class and continue from here in the next class. Thank you very much.